everybody, and welcome to the 2025 season of the Digital Series event. We've been having these event series, I guess, since a few years now, and initially it was a way for us to connect in between the conferences. And it was also the COVID time, but I guess everybody loved it so much that they wanted to just keep it. So we're here back again in a new year. A lot of things have happened. Speaking of a lot of things, we do have quite some society announcement towards the end of this presentation. But I guess what is important right now, which I want to bring up at the start, is that if you're planning to go to the ISTVS 2025 conference, then the abstracts are due this Sunday on 15th March. So do give a look at that. The call for papers link should be there in your as a notification for you. But we have a conference coming up in New Hampshire later towards this year. Do take a look at that. Again, abstracts are due March 15th, so we don't have too much time. But anyway, more society announcements towards the end. Let's get into why we're here in the first place. I'm going to introduce the host for today. The host for today is Professor Mehari Tekeste. I'm sure a lot of you already know him, but just a little bit about him. He is the director of the Soil Machine and Dynamics Laboratory at Iowa State University. He's been the editor of the Journal of Terramechanics for quite some time, and he's also been on the guest editor for some special editions. I guess there's a special edition going on right now, too, for which he's the guest editor. But in general, his research focuses on physical systems modeling and simulation of agricultural off-road machinery systems. And not only does he use modeling techniques like FEM and DEM, but he also does a lot of experimental testing to understand soil and crop to machine interactions. So join us as we welcome Professor Tekeste to host this session.
Yes, thank you very much for creating this opportunity digital event series at ISTVS 2025. So for today, we have two presenters and a brief introduction from myself about simulation-driven optimization of bulldozer blade and subsoiler or reaper design for digital twins of earth-moving machinery. The presenters would be Mohamed Abdeldayem, a PhD candidate at Mechanical Engineering Department at Iowa State University. He had joined our group, about 2.5 years, trying to do simulation-driven and similitude scaling law for modeling a bulldozer to soil interaction. Dr. Sedara just finished his PhD. He's now a postdoctoral research associate at University of Wisconsin-Madison. He had worked on optimization of a subsoiler design for wet soils on disturbed agricultural soils. The topic will be on simulation-driven optimization of subsoiler blade and reaper design. The ultimate goal will be for advancing the simulation-driven into a digital twin development of earth-moving machinery. Like I mentioned, the lab has 3 state-of-the-art for mobility testing, ground engaging tools testing, and accelerated wear. The instruments can be run automated or manual mode to process the soil, and also run the experiment using a single tire tester dyno and the single blade dyno instrumentation. This is just a picture of what we describe about our group. I think this is where we stop. So at the lab, we provide innovative testing methods for terramechanics or soil mechanics behavior as soil interacts with either mobile systems or ground engaging. This will be for mobility systems. Really, the key goal is to be able to derive a physics-based simulation and modeling calibrated to soil condition or soil type and validate to the nature of the test or the mobility system. The test data and our modeling capability could support finite element or DEM-based approach. We also leverage, reduced fidelity modeling techniques that deploy similitude or equilibrium analysis of force on a soil system. The ground engaging tools is tools that interact with the soil, mainly to loosen it and to move it, which is key for developing a digital twin of ground engaging tools, either for design optimization or doing a virtual environment for digital twin development. So for in the soil to any kind of tool interaction, there are different approaches, computer-driven or simulation, where the soil would be characterized through a constitutive law. It could be a CFD finite element, SPH, and DEM. What we found over the years in our group is DEM really characterizes the soil better because of its discretized nature of it. Field testing are still valuable, maybe at a reduced cycle. The labs that we have in our lab, we use them to validate simulation and modeling. Historically, analytical models have been used, and a lot of the reduced or fast simulation driven, they're still implemented, but they have a key limitation where it does not capture the failures of the soil under different initial conditions of the soil. For example, changing, bulk density or moisture content, you cannot always assume the failure shape. In this case, from Mackay was a triangle. For Terzaghi and Rees, it's logarithmic spirals. Those are not always accurate when you work with soil. For any kind of computational modeling, there is a step where you need to choose the material model of the soil in this case. So in our lab, we've been developing soil models for different finite element and DEM. We start building a soil model database. The test that Mohamed and Dr. Sedara would share will be using our simulant artificial soil. So the artificial soil that we have at Iowa State has a cohesion and frictional properties in terms of its bulk shear strength properties. It falls within the clay loam spectrum. What I mean by that is, if you measure a direct shear test or triaxial test, you would have a cohesion and soil frictional angles or frictional coefficient. The soil is varying within 7 to 11% from 5 natural soils that we have tested from Midwest area. So the advantage of it is it captures both cohesion and friction properties of soil, and it's repeatable to do tests with minimum error caused due to like a moisture content, for example, because it does not have moisture on it. By leveraging the simulant soils and validating different constitutive soil models, we will try to provide that key part in simulation-driven, the physics that soil is captured accurately. An example is what you would see a tire track. So the behavior of a tire rut formation mimics very closely to a typical field condition where agricultural machines will operate. Not extremely wet or extremely dry, but somewhere close to 10% of a plastic limit on loam soil. This is just an example of a cone penetrometer. We also use that in our lab. So I will try to pass now to the two topics. Our goal with this simulation and modeling driven is to be able to do a physics-based validation and development of models for earth moving applications. This is an example from CM Lab. They have a software to simulate a full machine. We are aiming to develop the interaction parts of the soil. And then the other talk that Dr. Sedara is going to talk is subsoiling, which is very common in ag applications. When there's a compaction or a hard pond is formed, you would need to use a shank. When you pull subsoilers on wet soils, the soil does not rupture because it's in its plastic state. So Dr. Adera's PhD was to optimize a subsoiler that would be useful to rupture soil under wet soil conditions. So those are the two areas that the following presentations by Mohamed and Dr. Sedara. So now I'll pass it to Mohamed.
Okay. So I'm going to talk first about integrating discrete element method and scaling law modeling technique for simulation of earth moving application. The picture on the left here, we can see many earth moving machine in a construction site. If we focus on this machine, we can see different ground engagement tools as blades, buckets, chains, and also different mobility systems as crawlers and tires. Focusing on the picture on the right, this is a picture for the D3K2XL bulldozer. A bulldozer machine mainly is manufactured to cut and push soil with a blade. And also sometimes it has a ribber in the back for loosening the soil. The main two systems interacting with soil here is the blade, the bulldozer blade, and the crawler. Of course, soil is not a homogeneous material, it's a heterogeneous material. It comes with different shapes, different types, different properties. Here I'm going to talk about the product design cycle. The traditional design cycle starts with concept, then design, physical prototype manufacturing, and testing the physical prototype, then launching the product to the market. My work here is to try to integrate the simulation-driven design to the traditional design cycle in order to reduce the cost and time for producing new blades. This video is from CM Lab. It's a virtual environment for testing a bulldozer machine cutting on the soil. The gap that we are seeing here is a lack of physical calibration and validation for the soil model used in these virtual environments. So to develop a physics-based simulation for a bulldozer machine, first I need some experimental data to validate my model. So the first part here is my experimental work using similitude scaling model of blade-soil interaction for 5 scale geometrical blades to predict some performance characteristics of a bulldozer, such as reaction forces and productivity. Lambda in my work here represent the blade geometrical scale. Focusing on this picture on the left, the width for the full blade is about 2,646 millimeters. In my work, I'm using 5 scaled blades with different blade scale starting from lambda equal to 1 to the 8th and ending with lambda equal to 1 to the 15th. For my biggest scale here, lambda equal 1 to the 8th, the blade width is 330 millimeters. To test my 5 scaled blades, I used a soil bin in the Soil Machine Dynamic Laboratory here at Iowa State. Soil bin is a box filled with our soil, our cohesive friction artificial soil, the soil simulant that we are using in our lab. And also the soil bin has 2 main carrots. The soil preparation carrot, which have a pillar, a pneumatic compactor, and a leveling tool, also a bucket to prepare the soil bed before testing. Also, we have a dyno test carrot mounted on the soil bin, which we are seeing here on the left. This is where I mount my 5 scaled blades or any different type of ground engagement tool to test it on the soil bin. LabVIEW Automated and MATLAB Simulink was used to control the soil bin testing. The working parameters such as cutting depth, traveling speed, and angle of attack could be changed, and also the results is recorded. My responses that I measured here is the soil reaction forces and the productivity, which is the soil mass in front of the blade after reaching the steady state. I used these two responses from my experimental work to validate the discrete element model of soil to blade interaction. This is a sample of the responses that I measured from the soil bin testing of the 5 scaled blades. Here we can see the reaction forces as a function of the travel distance for the different blades, for the 1 to the 8 blades and ending to the 1 to the 15, and also the soil mass that I measured as a productivity indicator. After analyzing the results, I was able to establish a scaling law to predict reaction forces as a function of the blade geometrical scale. This figure shows the lab measured log force ratio versus the predicted log force ratio. I found that my scaling exponent from the soil bin experiment, beta 1, is 2.57. Theoretically, the scaling exponent beta 1 is 3 if we applied the prototype to model similarity. But due to the distortion, the measured scaling exponent here is 2.57. Similarly, with the machine productivity, I established the scaling law predicting the soil mass as a function of the blade geometrical scale. In terms of the machine productivity, I found that there is 2 traditional methods to predict the blade volumetric load. The first method is the soil mass and loose bulk density. In this method, an experienced operator will run the machine, a bulldozer machine, for a certain distance, and the blade volumetric load is estimated by loading this soil mass in a truck, and the soil mass is estimated by subtracting the empty truck weight from the loaded truck weight. And with the information about the loose soil bulk density, the blade volumetric load is estimated. The second method depends on measuring the pile dimension, where an experienced operator will run the machine for a certain distance, and the pile dimensions as width and length and height is measured, and using this equation, the blade volumetric load is estimated. In purpose to integrate this discrete element model and productivity in a digital twin, we suggesting using a 3D reconstructed photogrammetry method, which we developed in our lab here, to estimate the blade volumetric load. Before applying this method to the soil bin blade testing, first we validated the method. Our validation depends on creating a known volume for a pyramid of soil, and then applying the 3D reconstructed photogrammetry method on it, and measure the error between the volume estimation from the 3D reconstructed photogrammetry and the actual volume. We find that the 3D reconstructed photogrammetry method estimated the volume with a percentage of error 4%. The next step is to apply the 3D reconstructed photogrammetry method on the blade testing experiment. This graph showing the results for the blade volumetric load estimated using the 2 traditional methods and the 3D reconstructed photogrammetry method. All of these measurements have been done at the Soil Machine Dynamics Laboratory for the different blade scales. After obtaining my responses from the experimental work, the next part is about developing a discrete element simulation of soil to blade interaction for predicting soil reaction forces and the blade soil load. To develop a discrete element model, we are going through 3 main steps. The first step is the soil characterization and contact model selection. In this step, we are characterizing and measuring some properties for the soil simulate that we are using in our experimental work, which is the cohesive friction artificial soil. And also, we are selecting the contact model that's able to capture the behavior of our soil. In the case of the cohesive friction artificial soil, based on the physics of this soil, we find that the Edinburgh elasto-plastic adhesive contact model, which accounts for the pre-cohesion and the elasto-plastic behavior of the soil, and also the stress history dependent parameters, which are an important parameters for any cohesive material, is the most suitable contact model to capture the behavior of our soil. The next step of developing the discrete element contact model is the calibration process. The number of the discrete element input parameter of the Edinburgh elasto-plastic adhesive contact model is 19 DN input parameters. We are not able to measure all these input parameters. So here we are using a simple lab test, the uniaxial confined compression test, to tune these parameters to make sure that our discrete element model are able to capture the soil behavior. The results we are seeing here at the bottom is after calibrating the discrete element model. The dashed dot red line represents the discrete element predictions for the stresses on the plunger base compared to the experimental data, and after the calibration, we were able to reduce the error, and we can see a good matching between the discrete element predictions and the lab measured data. The last step is to validate the discrete element model using 3 different blades. The first blade on the left is the narrow planar blade. In this blade, we tested this blade at the soil machine dynamic laboratory and also measured the responses as soil reaction forces and soil mass. And we can see that in our discrete element model, it was able to capture the soil failure compared to the Makaya theory. But to make sure that my discrete element model is able to capture the bulk behavior, I validated the discrete element model using another blade, a wider planar blade, to include more bulk material behavior. And also, because of there is a gap with the analytical method, which doesn't account for the complexity for the blade design, and to make sure that the discrete element able to capture the complexity of the blade design, the third validation test was done using 1⁸ geometrically scaled curved blade. Based on these results, we found that the discrete element model was able to capture the slow flow behavior compared to the experimental data. Also, the discrete element model was able to predict the soil reaction forces with 11% relative error compared to the lab measured data. And also, the blade load soil mass was predicted using the discrete element model with a 24% relative error compared to the lab measured data. This calibrated and validated discrete element model shows a potential for machine ground engagement tool development as accelerating the design analysis, reducing the physical testing, and also modeling earth moving operation using digital twin by integrating this model with other computer-aided engineering tools. In conclusion, a strong correlation was established experimentally between the logarithmic relationship of the 5-blade geometrical scale ratio and both the steady-state soil draft force and the blade soil mass ratio with a high coefficient determination of 0.988 and 0.99 respectively. A new 3D photogrammetry-based reconstruction method for estimating blade volumetric load has been implemented to analyze bulldozer performance. This approach offers distinct advantage over traditional field measurement technique and can be integrated to develop digital twin and enable real-time AI algorithmic training for earth-moving machines. Discrete element predicting soil draft force and bulldozed soil mass at full blade load at percent relative error of 11% and 24% respectively, when average over narrow blade, wide planar blade, and 1⁸ geometrically scaled blade. I would like to thank my colleagues at the Soil Machine Dynamic Laboratory, Nick, Adewale, and also William Sadler for supporting my work. And also I would like to thank Ben and Tom from Caterpillar for training for LabVIEW using. and Altair Eden for the license and tutorial support. For more information about the experimental work and the discrete element development, you can check our publications. We have 2 publications at the Journal of Thermomechanics, one of them about the experimental work and one of them about the discrete element modeling. Now, I think we are able to move to Dr. Sedara to start presenting about the subsoiler design.
Yeah, thank you. Thank you, Mohamed. So, Dr. Sedara, are you on the online? Hello?
I'm online. Can you hear me?
You're a little, I guess, far away from the speaker.
Can you hear me?
It's better now. Yep.
There's an echo.
Okay.
There's some background noise.
Yeah.
What of now?
Ah, that's good.
Yeah.
Okay.
Okay. Yeah, thank you. Go ahead. So we can have the questions and discussions at the end. Is that okay to do that, Bersha?
Yes, we shall do that.
Thank you.
Okay. So thank you for giving me this opportunity to share my research, my PhD research, to add to the body of knowledge. I'll be speaking on applying similitude and integrated discrete element method for parallel subsoiler design for the subsoils. Initially, what brought about this was that there is a special operation that when the soil has been disturbed by construction activities, how long does the farmer wait? How long does the farmer wait for the disturbed soil to return back to its original or undisturbed soil? So this was the question, and this brought about that there is a need for us to develop a special tool for accelerating this process. So we took the advantage of the discrete elements modeling and virtual simulations. And then we considered numerical methods, which are finite element methods and discrete element methods. Next. So what we did was we considered the industry current benchmark, the John Deere standard 2730 combined and the CNH 875 Dix Reaper. These were the current benchmark we used for the basis for our design. These were the ones that were used on the field that we studied for a year. I carried out a study on the field and observed that using this current benchmark Dix Reaper on the field has not been able to reduce the soil compaction at the subsoil and then the wet condition. So there is a need for us to improve this design or to produce or develop a new kind of tillage tool that can help us reduce soil compaction at the subsoil. Next. So what's the motivation for the development for this methodology? So there's a deep tillage, a reaper that has been used. It was used at 18 inches deep on the soil. And we observed that there was an activity, it's a pipeline activity. So the topsoil was removed, then the subsoiler was used, then the topsoil was removed. Then there was a lot of tillage management for us to remediate the soil, but still the soil compaction still persists. So if you look at the diagram by the left hand side, you see the shape. There's a poor performance at the shallow critical depth. So if you look at that soil rupture below soil rupture, the shape shows you that there's still soil compaction at that stage. So there's a need for us to reduce that. So the current development was, what do we propose? That since there was subsoiler that has been used over the years and it has not been able to be effective in the wet and deep below critical soil depth, so there is a need for us to develop something. So we used the similitude soybean study approach to optimize a shank to improve soil health, or to improve the soil in terms of reducing soil compaction. And we considered from literature existing work that has been done on how the ground engaging tools for loosening granular materials, soil materials, agriculture, the applications that have been used, considering the shanks, the straight shank, the ripple point shank, and different shanks, and how they have been able to the loosening of the soil, how it is captured. So this is what is shown in the diagram on the left and the diagram on the right, showing us the draft from a kind of from REPA 2025. It was the research that was carried out, and he brought in some designs from the market and tested it in the lab, and these were the results. The result shows that the Roman figure 2 and Roman figure 1 gave them in terms of draft, there was 28% reduction, but in terms of the total, the trench cross-sectional area, there was 33.2% reduction too. So this was the experiment that was carried out that is existing in the literature. So there is a need for us to also look at coming up with a new design that can help us to reduce more of that. So the ripper shanks and blade in construction. So just like my previous speaker just said, he is working on the blade, while me I'm considering on the ripper below. So this also helps in terms of how does these two interact. Next. So the approach we are using discrete element method. First, initially, I came up with a kind of a design, a car design. I came up with 12 designs, 12 car designs. Then I use taking advantage of discrete element method to reduce the design to 6. So the 12 design was reduced based on the DEM soil horizontal draft force and also the soil bulk density difference. These were the criteria we used. We used the ratio of this criteria to reduce the scaled shanks to 6 cards. These were developed next. So this was developed and taken into the soil engaging soybean at the soil machine dynamic laboratory. Just like what I said initially, these were scaled shanks. They were scaled down just to enable us to be able to work with it experimentally in a soybean. So the soybean was 7,420 millimeter wide in length and 690 millimeter wide and 150 millimeter deep. This was the dimension of the soybean. And the soil characteristics type was, it has a cohesive frictional artificial soil. That's what we used, with an apparent cohesion of 18 kilopascal and soil to soil friction angle of 30 degrees. So the soil processing was done to prepare the soil in the type of condition that we want. So we measured the soil bulk density. It was 1.48 megagram per meter cube, which is with a standard deviation of 0.2, so it's over a sample size of 5. So we took after the soil was prepared, we took different samples to measure the soil bulk density to know the condition of the soil. So the tools were run at a true depth of 83.3 millimeters with a constant speed of 268 millimeter per second. Next. And the design of experiment, we did a design of experiment for the shanks, and each shank was run in 3 replicates, and these were the responses we measured. Using the lab view, we measured the soil reaction forces, which is the horizontal force Fx, and also the vertical force Fy. And below soil loosening, we have the critical core depth, soil depth, which is D1, the spoil cross-sectional area, the trench width, and also the soil rupture area. Next. So these were the results that were obtained. So we observed that there was significant difference. The shanks have the significant difference on both the soil horizontal force and also the soil vertical force, with shank 3 and shank 2 giving us the lowest in terms of horizontal force, and also we also observed that in 2 and 3 also give us lower forces in terms of shank 5 give us lower forces in terms of soil vertical force. Next, this was also observed that there was significant difference of the shank affecting both the spoil cross-sectional area, the trench width, and also the soil rupture area. This was also observed across these responses. Next. Also for the below ground disturbance, which is the critical core depth, soil depth, and also the soil core depth before the critical core depth is D2, the D1 and the D2. So we observe that shank 3 gave us the highest value of critical depth, and also shank 3 also gave us the lowest in terms of below the ground, below the critical depth. So when we also try to capture this using the simulation, just to show the interaction between the experimental and the virtual environment. So we ran the simulation using the DM soil model. We created a soil model, we calibrated it and validated it, and we tried to run our shanks. So we observed that we tested the shank 1. Shank 1 is a straight shank. The shank 2 is a bent shank, which is raked shank, while shank 3 is a power plow with an angle of okay. So what we observed that in terms of maximum soil rupture, because the aim was to have a shank that can help us reduce draft and maximize soil rupture. So we observed that shank 3 was able to give us a maximized soil rupture and a reduced draft, which is very good for us to upscale and go into building the prototype, developing the prototype. So this was what I did for my PhD. And in conclusion, 6 top-ranked scale shanks were manufactured and tested in a soybean lab, and measuring energy parameters such as the horizontal and vertical forces and soil loosening responses, above ground and below ground disturbance, bulk density changes, and an overall analysis was carried out to identify the optimal shank design, which was the shank 3, as the best for minimizing energy use and maximizing soil loosening. And discrete element method-based design scaled shanks were also evaluated to accelerate the shank designs based on soil to shank interactions and the responses of the soil reaction forces and soil loosening responses. Next, I would like to acknowledge the Dakota Access Pipeline for funding this research, and it was also partially funded by the National Science Foundation, NSF, for funding this study. Additionally, I will also want to recognize the Soil Machine Dynamics Laboratory research team for their support on the field and when I was doing the field experiment. And I also want to thank, and I'm also thankful for the support received from Nick Parmesher, who is our technician at the SMDL lab, and also in assisting me in the soybean studies. I would also like to thank Sheriff John, which was our laboratory coordinator at the Department of Agriculture and Biosystems Engineering at Iowa State University, Ames, Iowa, for supporting the manufacturing of the shanks. Thank you. The publication has been made on this at the Journal of Thermomechanics. If you want more information about it, so you can also check it out. Optimization of subsoiler design using similitude-based discrete element simulation and soybean testing on cohesive frictional artificial soil. Thank you.
All right, thank you very much. Let's see if we can go to the window session where we could see chat or anything. So, Rochelle, how do you want to handle the questions or discussions?
Well, I'm going to request the audience to send your questions in the chat. If you also want to be called up on stage, I need to allow you to do that. So please request if you have a question, I'll call you guys up on stage. Okay, well, I was going to get a question, but we have quite some question from Joseph. So Joseph is asking, what approach do you follow to select or calibrate realistic particle scale properties as the input to the DEM simulations, considering that multiple material parameters are involved in soil constitutive relations? And I guess this is also one of the questions that I had too, because especially when you're starting with simulations like DEM, it could be really tricky to parameterize these type of models. So what are your thoughts on something like that?
So, okay. Mainly, I focused on not all the 19 DM input parameters. I checked the literature, then I find that like about 9 DM input parameters are the most ambiguous one. And still it's high number of DM input parameters. I applied a screening using Blackett-Berman screening method to screen these parameters to see which ones are more affecting the results. And endly, it was like 5 DM input parameters at most affecting the results.
Okay.
Yes.
So it was like a sensitivity study just based off of like the material input parameters, right?
Yep. Screening first for the DM input parameter, then focusing on a lower number, and I used central composite design to have mental model and optimize the input parameter based on the results that I measured, the responses that I measured from the lab tests, such as uniaxial confined compression test. I'm still working in tuning the calibration process with adding more tests to reduce the error that still we are seeing in the soil mass, especially the Bulldozer soil mass.
Right.
Yep. And still in the publication process.
Yeah. I guess one of the things that I face is like sometimes when you have a lot of input parameters, it comes down to how unique are these input parameters for, that test, because you can probably change a lot of stuff. So I always focus on that. So what are your thoughts on something like that?
I'm usually going for I will do some preliminary testing using a simple test. And then, as I told you, I will focus on the most sensitive ones.
Sensitive ones, right.
Yeah, most sensitive ones. For my contact model, I find that if for the Edinburgh elasto-plastic, you will find that there is some coefficient related to the pre-cohesion, the pre-cohesion force, and also the elasto-plastic behavior of the soil. These are more, I find these are more effective. Also, the shear modulus for your material, the coefficient, of course, the interactions, interaction between particles, interaction between geometry, depends on the application. So I find that the interaction between particles are more affecting the results for my case. So I focused on these 5 parameters for more calibration.
Right. No, that makes sense. And I think that's really a good insight that you gave us, because sometimes when you start DEM, you don't know where to start with because you have so many parameters and you have to parameterize them. So that's a good question. Another question that we have is, in a typical wheel-soil interaction analysis, how many particles do you typically use? What are the shape of these particles in the simulation?
In my case here, we were lucky to have a close look to our particles. It's not like completely spherical, but I assume this like a spherical.
Okay.
And by tuning the interaction properties, you can overcome this. And also by applying a rolling resistance model with the Edinburgh elasto-plastic adhesive contact model, this is adding it's adding a momentum to resist the rolling due to using of single spheres. I tried to use multiple spheres and different shapes, but it was really computationally expensive, and it doesn't have much effect on the results. So instead of this, I used a rolling model and calibrated the model parameters to make sure I'm capturing the same behavior.
Okay.
So just a simplification for the shape.
So what was the computational time like? Because you said that with, because I know if you change the shape of the DEM particles, the contact algorithm just gets so expensive. So what was the difference in the computational time? What did it take for your simulations, and what typical range were you seeing for if you like just change like the particle shape?
So at the beginning, I used a single sphere and 3 spheres.
Okay.
This is at the early stages for the preliminary simulation.
Okay.
I don't actually recall what the time, because this has been done like something, but I think it was like three times.
Three times.
Yeah. So and it was for a simple test, not for the blade testing. The blade testing had more particle numbers. So it was just a simple test for an angle of repose test. A simple test was like 50,000 parameters. It was like very consuming. In the blade simulation, I'm using around like 700,000 particles in the simulation. So you can see
how much time does it typically take? Like when you fire up the simulation, how much time do you gotta wait to just see the results?
I think it depends on the hardware that we are using. So luckily we're using some workstation with GPUs. The GPUs
it's GPU accelerated.
Yes, it has a huge impact in reducing the computational time. For the blade simulation, it could take within a reasonable GPU card, it could take like 3 hours. For the blade simulation.
That's not bad. Okay. So another question that we have is, can you explain? Let me see. Can you explain a bit more on what digital twin tools were used to integrate in your DEM outputs?
Yeah, I think this is a very good question. Okay, we're still doing a research on it. Right now, the focus was, can we validate the physics with the scaling law or with the soil? So what we have been working behind to continue this research is, how do you develop a reduced physics model so you can integrate it into a full-scale digital twin? So the parameters in the digital twin for this application could be so many things. Blades performance is affected by the rake, the cutting depth, the speed, and the power, tilt and angle. All those optimizing parameters that a machine operator could do, we will try to include them into the digital twin. I know that, it's very challenging to do a full scale at the field to validate that at a high fidelity with the digital twin. But this scaled law allowed, our research to establish the scaling law relationship. So if you think about a scaling law, you're trying to obey, dynamic similarity, geometric similarity, material similarity. The ratio of forces is proportional to a cubic of the length scale. So for Mohamed's work, the exponent was 2.57, am I right? Yeah. So you cannot have it theoretical. It's very difficult because there's a lot of deviations from obeying the law, in particular the soil, because soil is assumed to be a distorted model. It's very difficult to obey all the similitude laws, but it's reasonable, for this. So that's the route, but that's a very good question. That's what we're trying to continue this research in the near future.
Yep. Well, that's a very good answer. And I guess that's what the whole world is also looking forward to, digital twins and all your simulations to be integrated and all bumped up with the use of AI. I guess that's what we're looking forward to. So it's really nice that you guys, because you have a test, bed for it. You have the simulation capabilities. You have the scaling law, which means that you don't need those big bulldozer data for any validation. You can easily do it. I think it's going to be a very good database in general, just for this type of activities. So going on further, Mr. Zamir asks, so Dr. Sedara, do you have DEM versus test overlays for the ripping force? And did you use the same calibration method as the previous study? For example, the confining compression, I think it was the uniaxial test. Was that the same way that you guys calibrated it?
Yes.
Yes. Okay. How was the?
Yeah. Hey, Zamir. That's so. I think it should be in the publication, but there's also one manuscript in development under review, looking into. So when you do calibration of soils, okay, you cannot simulate at the scale of the soil. You have to approach a certain inverse technique, both the scaling and the material behaviors. For this new article in development, Zamir, Adewale also used angle of repose. So the mechanics drives how to calibrate the behaviors. For example, for Mohamed, if you have a blade cutting a soil, the soil tends to have elasto-plastic strain. Our soil has cohesion, and it also have a bulk behavior. Once the soil post-failure, once the soil is failed and it's rolling like, you can assume like a rigid body with dynamic change in mass and shape, that is the flow. So we look flow, compressibility, and elasticity. For Dr. Sedara, we use it also the standard confined compression testing and angle of repose. Compenetrometer.
Oh, okay.
Yes. Yeah. So, Amir, that's very important because, in a field subsoiling application, you would go and measure compenetrometer if you know where the hard pan is, both in magnitude and location, then you could subsoil it. So because of that, and because sometimes soil in front of a compenetrometer have a cavity expansion, compenetrometer was also part of the calibration process. Am I right, Adewale?
Yep.
Yeah. I don't know if you had angle of repose too, but at least I remember compenetrometer and confined compression.
Yes, those are the two. Yeah.
Thank you, Zamir. Yes. The angle of repose was on Mohamed, because the material was flowing.
This is still in the publication. So we added more tests to enhance the calibration process and reduce the error. So I added angle of repose and assembly plate testing also. So I have like 3 tests. Turn it to a multi-objective optimization problem to find the DEM input parameters, the optimal ones. Yeah, but still, I hope it's coming to. It's published soon or something.
Yeah, no, I understand. I understand the position you're in. I completely understand. So we're going to go forward with the question. Professor Vladimir Vancevich wishes you the best. He had to leave, so he just wanted to put that out for you. The next question is, I think this is interesting. So was the blade or the soil, was the blade soil cutting speed a part of the model? And if so, could you speak on how scaling is applied to the speed? Thanks.
Okay, so in our case here, we fixed the speed.
Okay.
We fixed the speed for the 5 blade scales.
Okay.
Yeah.
So that's something that is yet to be studied.
Yes.
But it was a good. So one of the things that Mohamed's project, when you do solvent study, we use complete block design or randomized complete design.
Yeah,
So
yeah.
if you do that, the soil then is processed, and you have to reduce the confounding effect of processing the soil. So for that purpose, and for calibration, at least for this scaled blade, it helped us to do it in one speed to reduce the confounding effect in the experiment itself. And usually, errors propagate to, calibration and all that. But that is now the second step is, can you include a different speed? And we don't know what speed range. That's also another challenge. At least the scaling law is in the literature to match to big scale. But we still need to know how much is it deviating in the predicting the forces and soil mass. So, very good question, but there was a reason why we fixed it to one speed,
Right.
for the reason that we mentioned.
Right. Yeah, that makes sense. So again, another question from Mr. Zamir. So it would be interesting to break down your DEM, dosing reaction forces, into inertial, elasto-plastic, and shearing. This is significantly interesting because your method for calibration and validation using your confined compaction test, and yet you achieve reasonable agreement with DEM and the test. So would you be able to say with confidence that shearing has a small contribution to dosing and the reaction forces? So I think it goes back to the DEM input parameters. I know this is, I guess this is one of the main questions that people get about DEM is just the input parameters, because I know it's so tricky to get these input parameters to be right and calibrated. So what are your thoughts on this, Mohamed?
So this is not the last calibration process. So the error that we have here is still, it's not like the finalized. We have a better results for both reaction forces and soil mass using the multi-objective optimization.
Right.
About how the shearing is important, yes, I find that from the tuning of the parameter that shearing is important. Actually, and I could see this in the soil laboratory. The shearing is important because, or be it more important than the compaction, because we didn't compact the soil very hard. We reached like the compaction level that you can see in the natural soil tool interaction. Okay, but yet, yes, I see the shearing is still important for the reaction forces or for the blade soil interaction.
So I guess what you're trying to say.
Can you see the slide?
Yes. I pulled it up. Yep.
Yeah, very good. I think Mohamed was explaining about the fidelity or the level of accuracy. So Zamir, if you look at the accuracy of DEM with calibration using the uniaxial compression, you see the soil reaction forces, both in this case is horizontal, the draft, it's 11%. Okay, I think that's reasonably acceptable. Anything as close to 10 or less. Now, using only one, the uniaxial compression test, you could see the blade load mass prediction was 24%. Okay, what that shows is there's a room for improvement, which is partly due to that shear-driven soil mass accumulation. So in the last chapter of Mohamed's PhD work, he added angle of repose and also looking mass in front of the planar blades to add additional complex soil behaviors to drive the optimization into multi-physics behaviors, including the shear. So that work is already completed. So I don't recall the accuracy on the soil blade mass, but they came also less than 10%. Very close to it. Yeah. 12%. Yeah. So yeah, that's the trick about, and again, the goal is this, okay? All simulations are wrong. Except, right?
I love that. Yeah.
Yeah. The accuracy level of the simulation is what you try to accept.
Yes.
Even any mathematical model, whether it's experiment driven or simulation driven, has an error. Now, the fidelity or how much do you accept would vary. So the good thing is draft force on bulldozers is one of the key. Always when you think about DM models, a lot of DM constitutive models, we always have a challenge on calibrating mass or volume of materials piled, or vertical forces too, because those micro mechanics contact models, at least what we use, sometimes does not predict the vertical forces from tools. Yep, that's the thing is this fidelity improves as you bring multi-physics soil experiments for the optimization. But as you progress your quantification of accuracy, you're building both the reducing uncertainty and also improving accuracy to the different physics.
I think that's a very nice thing that you just said, because you broke it down into, like, it's not just the draft force that we're looking at. It's not, you're also seeing the vertical force, which you're telling me that it could be harder sometimes. And the soil mass, just to get the soil, the way that it ruptures, that could be hard to simulate too. So there's so many, what I'm getting is that there's so many aspects of this that you have to look at when you're looking at simulation, and it's very challenging. And I think it's very nice that you say this to our audience, because sometimes I don't see people saying this. So thank you for saying this, and to make sure that you're giving us realistic expectations. If somebody wants to start DM modeling or something, I think it's a very realistic expectation that you're setting, instead of saying everything works perfectly, because it's not really that way. So thank you for saying that. We have
even experimental test driven equation, they're the same. You just let the statistical model to assume a certain level of error and a certain distribution. So that the approach is not naive. It's but we need to make sure it has to be physics driven quantification of error and also uncertainty. I think the uncertainty could remain to be still a challenge, but at least for accuracy, that's the approach that we use in this experiment.
I completely agree with that. Going on to like the whole, having ranges for these solutions, and certainly quantifications, because experiments, sometimes they don't agree with experiments themselves. So I think that's very valuable. I remember somebody telling me that, especially in my preliminary defense, and told me to put bounds on my, solution, quantify the error. And I was like, yes, that's going to help quite a bit. So that was really, nice words that you said. I'm just going to go on, I think, two last questions. So Professor Keen is asking, what are the results in comparison with more of these analytical type of models? And can you quantify their improvement? And where do you think the improvement comes in, I guess? So.
Thanks, Professor Alex. Let's see what the PhD candidates say about that, okay?
Okay. So I compared it to Makaya's approach, not Rees' equation. For the blade, yes. They are kind of similar, but Makaya's approach is like more simplified for the, especially for the n factors estimation. And actually, it was a little bit far from both DEM and experimental results. So the Mackay's approach was over-predicting the draft forces. Yes. I think, Goodwin, this is a question for Adewale about the river. For the fundamental earth-moving equation by Rees and Hitirashi, also I find in literature that they said it's usually overestimating the reaction forces. So I mainly focused here on validating my discrete element model using the experimental data. I didn't try to validate using, because I already have experimental, so to extend it to analytical, maybe we could consider this in the future to benchmark between the different analytical method, either the fundamental earth moving equation or Mackay's model.
Okay. But what do you think is, what would your DEM model have that these type of models, what is that main assumption that you feel that, what is that main assumption?
Yeah, I think the main assumption is the blade geometrical complexity.
Right, okay.
So, yeah, here we are using curved blade. DEM also can model curved blade, and this complexity can be captured for both DEM and experimental. But the analytical models doesn't have this assumption for, doesn't include the blade complex geometry. And also the failure plane, there is assumption about the failure plane with the analytical models. We don't have these assumptions here. We just let the physics lead the failure.
Right.
Yes, and as Dr. Mehari said, we are doing this within a certain error. So we set through our calibration flowchart that if we could achieve reaction forces within a 10% relative error, this is acceptable for us. And also for the soil mass, we set a threshold like 15%. And after the rigorous calibration we did, and we're achieving this.
Yeah.
I think one thing that Professor Alex, maybe you could also continue this discussion from your own opinion. I think those models are great. When we do the digital twin, we may need to go back to them to see how much fidelity is included. Now, for sure, to my recollection and reviewing it with my students, those empirical models, they don't quantify the soil mass cut by tools.
Yeah.
They predict only forces.
You're right.
So that is at least the key improvement that you're going to get from high fidelity, because bulldozers, any kind of off-road machineries, wheel loaders, their productivity is measured, even their cost many times is by how much mass they transport per unit time or volume of soil to move, or any kind of granular material. So that's really the key that simulation driven is allowing us to do. What's so good about them is, I think at the fundamental, if like what Mohamed mentioned, if shape is the same, if the initial soil conditions are very close, I think both of them, either using this rapid empirical equations versus fidelity and benchmark it to experiments, they should be able to get as close to each other. But the thing is that because I think part of it is because of the lack of that failure assumption that you make, depending on the initial soil condition, the shape of the tool, and the inability to do soil mass with the empirical models.
Yeah.
Dr. Alex, anything to add to that thought process?
Yes.
Or comments, please?
Am I? Can you hear me? Okay.
Yes.
Great. Yeah. Thanks for that. I mean, there's some interesting comments there. Obviously, up to 20, 30 years ago, that was what we had to work with, and I don't know if you remember that Dick Godwin at Cranfield and some of his colleagues, they produced some spreadsheets using those equations, and I've used them to model timed implements, and then built trapped implement models and then put them through different conditions to try and look at performance and so on. And the good thing is it's quick. If you put it into a mathematical model spreadsheet, then you can play with the numbers, you can get data out, and you can, the big question is how good is the output and the quality of the information I'm getting from those sorts of models. The reality is that if you go into a field with a subsoiler or a tine, then the soil conditions are continuously changing. And most of the experimental work that we tend to do in soil tanks and bins, we try desperately to make the soil as homogeneous as possible or repeatable for tests. The reality is when you get in the field, particularly in England, the soil will change every few meters. You're getting changes in soil quality. Some parts of Europe, that isn't the case. You get very good repeatability across very large areas. So I suppose the general question is, how do we take either the Seterace Godwin data or the data that you're generating, how are we going to apply that into tractor implement combinations to try and actually look at problems or to improve designs? I don't know if you've got any general comments, or whether that is a longer term or a medium term objective of what you're trying to do, or how far you think you have got in this time frame.
Yeah, I think Dr. Adewale is now in the University of Wisconsin. You see, for the power requirement for ag tillage applications, I think there's a good reason for using those rapid mathematical predictions, provided that there's a good soil parameters to find for a particular type of region or condition that the tractors are intended to use for either power requirements. I think there's still, either of the approaches are reasonable as long as the prediction accuracy is quantified. What Adewale did during his PhD work is to quantify the rupture area below the ground. How much area are you rupturing when you change the shank, and how much are you spoiling or building above the original soil surface. Still, those models cannot predict that, because that's what we call that soil loosening part of a design. The power requirement, I think the draft, those empirical models are still useful once the soil parameters are measured or optimized. But if the intent is for design to look at what's your design purpose, if it's to loosen the soil below ground with a certain achievement by percentage, with benchmarking it, you can't use those models. That I think Godwin had some empirical based on what he called the rupture distance and critical depths. But I think the DEM is way faster now. Still not to compare them in Excel sheet versus DEM, but faster enough to be able to give you a high fidelity about the soil loosening part of subsoiler shanks.
Okay, thank you.
Yeah, I think that was a good response to that, because I feel like with DEM, there's so many things that you can probably quantify. And again, it's up to what the objective is at the end of the day, what the project is at the end of the day, on which method to probably go for. But I do think that, having results with DEM, because sometimes, at some time, the low fidelity and the high fidelity world meets. And we'll see when it will meet. And I see that you're on the track and the journey for that. I'm thinking that years down the line, you'll have your own Excel sheet where, you know, you have all that data that you get from all those simulations, and you have your own model, which is all, you know, based off of the data that you've collected from the simulations, validated in your test rigs. So we'll have more models coming up for, you know, fast use in the future. That's what I can see from your lab, right?
Yes, thank you. Yeah.
Cheers, thank you.
Yeah, Alex, that's the near future. I think where we're going to come is, you know, we could have somewhat hybrid reduced versus high fidelity, simulation driven or whatever AI driven. Then you could have a library of choices to do.
Right. Yep. Well,
okay.
That sounds good. You have a lot of thanks and appreciations in the chat. But I guess, well, that's all there is for the questions for you guys. I think it was a really nice session. And I must say, very realistic, you know, observations that you're giving us. And I think it's very valuable to the community, you know, because these things are only things that you can get to know when you talk to a person one-on-one. So going forward, I want to thank our speakers for today. I think it was a very interesting presentation. The questions, you know, the Q&A round was really good. You could see the interest that people actually have in, you know, in this area. So I guess it's going to be a very important area coming up, you know, for the Army, for the agricultural world, for everybody. So moving on, just with a few society announcements that we have. First of all, well, if you don't know, we have the ISTVS 2025 conference coming up. It's the 55th conference that we're having. It's in New Hampshire, USA. It's organized by CREL, which is a part of ERDEC. So the U.S. Army Corps of Engineers. Please do check it out. You know, the call for proposals is out. The abstracts are due soon. So go check that out. See all the, you know, there's some theme. The full paper is due, by the way, May 15th. I think that's what the day is. And yeah, the conference is on October 6th to 9th. So I hope you put that in your schedule and we can meet there. Also, we have a few more announcements. We have an ISTVS ISU symposium on turbo mechanics in agricultural soil vehicle systems. This is in Iowa State University, and Professor Tekeste is organizing this. Do you have a few words on this, Professor, since you're here? And I would like for you to introduce our society to this.
Yeah, well, you put me on spot. Okay. Yeah, thank you again. I think what the ISTVS as a society, what we're promoting is, you know, how do we, as a society, see the link to an agricultural soil conditions with the vehicle systems in an agricultural application. We have seen a lot of trend in the ag industry where machines getting bigger and new tire technologies, track technologies are in the market. So at this symposium, part of the intent is to bring technical sessions and attendees from industry, from the Midwest area, or even far distance. And having this symposium is going to also introduce the society, so people would plan on attending the event in October to, you know, for the American conference. So it's kind of a precursor to our annual conference in New Hampshire, and also bringing the agricultural soil vehicle systems. The president of ISTVS, Dr. Luth, supported this program, and he's a champion for this too. Thanks, Bersh.
Okay, we'll have more information coming out about this. You'll also get some emails about this, but you keep your eye out. Mark your calendar for May 21st of this year. We're going to be having the first symposium here at Iowa State University. A few more announcements just before you leave. Of course, all these videos that you're seeing, all the seminars are recorded and put onto our YouTube site. And you can see here, the channel for this, the previous, speakers we've had, on all of that. So I will be uploading this, in the next coming week in case you missed parts of it to our YouTube site. So please do go and access it there. Further, join the society. We do a lot of stuff, a lot of fun events in between. If you go and subscribe, you will be getting email notifications about everything that's happening. It's not just the conferences that we do. There's a lot of other stuff that goes on in between. So with this, I would like to end this event. We will be having another DES event coming up next month. It will also be hosted by Professor Tekeste, hopefully. But stay tuned for that. I will be sending some notifications out for that event too. So thank you, everybody. Thank you to the speakers. And thank you for joining us today for this session.
Thank you. Yeah, thank you. Thank you, Dusha, for leading this effort, the digital effort. We look forward to continue working as an ISTVS community. Thank you.
Sounds good. Thank you so much.